a shear thinning behavior, and to explore the effectiveness of the hybrid nanofluid in the microchannel heat sink. In the present work, the microchannel heat sink for the analysis was adopted from Q and Mudwar from 2002. Here, the properties of water, which is the base fluid, is considered as a function of temperature as per the correlation that is given here. Also, the values of density and specific heat capacity are calculated in classical models. For the purpose of thermal conductivity, the correlation given by Zhu in 2005 is being used, which is given here. Now, for evaluation of viscosity of nanofluids for spherical nanoparticles, the Brinkman equation is very popular, which is given here. But the CNT nanofluids have a non-Newtonian behavior, so Brinkman equation cannot be used. So the viscosity for CNT nanofluid is given by non-Newtonian power law, where the flow consistency index and the flow behavior index was evaluated by the Levy ETL using the experimental data given at DIN ETL. So the EUDFs are written as per the correlations given here, and they were incorporated during the simulations. For the purpose of simulation, the mixture model is being used. So a mixture model is a two-phase model that considers coupling between the phases is strong, and within any control volume, both volume fraction of the primary phase and the secondary phase exist. So here the governing equations are written for a mixture of continuous and dispersed phases instead of writing separately for each phase. So the continuity momentum equations are given here, energy and the volume fraction equation, slip velocity and drift velocity. The mixture model employs a algebraic slip formulation, and according to marine ETL, the slip velocity is given here. The drag fraction is taken from the Schiller and Naumann, as given here. Now coming to numerical method, the simulations have been carried out in the ANSYS 15. ICM CFD is used for the mesh generation, but both solid and the fluid zones, quadratic hexahedral cells are used. According to Fedorov and Visconta, the high concentration of node near the entrance and the compact non-uniform grids near the walls were taken. Boundary conditions are as mentioned here. The solution method involves the use of simple algorithm. The second order point scheme is employed for momentum energy equation, while quick scheme is employed for the volume fraction. The convergence criteria is set to 10 to the power minus 6 for the continuity momentum equation, while 10 to the power minus 9 for the energy. Now coming to the data reduction, the rate of heat transfer to the fluid inside the microchannel is given here. For evaluation, the parameters such as average heat transfer coefficient, thermal resistance, and pumping power consumption as given here. Now coming to the validation of the model, the obtained numerical results with the experimental data for microchannel heatsink used for the experiments by Lee and Midwar in 2007 were used as it is shown in the figure. For the difference of the mean temperature with respect to mass flow rate is shown here. For the mass flow rate varying from 2 to 6 gram per second. You can see from the figure that the numerical with the for the grid independency test, the grid independency test is carried out for 2% volume fraction alumina at an inlet flow rate of 2 meter per second. From the grid independency test, 4.18 million mesh shells was selected for the further simulations. Now coming to the results, here we have compared the performance of mono water, the base fluid, the mono nanofluid, and the hybrid nanofluid. So from the figure you can see the increasing velocity. The hybrid nanofluid is showing better performance compared to the alumina nanofluid, the CNT nanofluid as well as the base fluid. Although the CNT is showing better performance than alumina and the base fluid. Now coming to the pressure drop, you can see for the lower velocity, the hybrid nanofluid is having a higher pressure drop. But as we move forward to higher velocities, the pressure drop is lower for the hybrid nanofluid. The reason behind this can be devoted to a decrease in viscosity with increasing shear rate, that is increasing fluid velocity, which is a characteristic of the shear thinning fluids. Now, if we compare the thermal resistance with the pumping power consumption, you can see the base fluid water is having a higher value of thermal resistance with respect to pumping power consumption. While if you see for a hybrid nanofluid, it is having the least thermal resistance for the pumping power with the pumping power consumption. From characteristic curves, we also get the information about the preeminence of the hybrid nanofluid over the mono nanofluid as well as the water as the working fluid. Now coming to the conclusions here, the the numerical simulations were carried out to compare the thermohydraulic performance of hybrid nanofluid with mono nanofluid, either alumina or CNT, and water as working fluid for the microchannel heatsink. According to the results mentioned, the conclusions are drawn that the hybrid nanofluid has better cooling performance. Due to high shear thinning behavior of CNT, the high pressure drop is observed for hybrid nanofluid at lower velocity, while the low pressure drop is reported.
Good morning to the respected chairperson and the audience. Title of my manuscript is Effect of Longitudinal Translation of Two-Out Type Vortex Generators on Wake Modifications and Fin Tube Heat Exchange. This is the presentation outline. Let me first begin with the motivation and the application. In heat exchanger industry, heat transfer enhancement is an essential way to control the unit cost. It helps in reducing both material and manufacturing.
Respected session chairs, delegates, presenters, organizers, warm greetings to all of you. This is Yogesh Kumar Prajapati, Assistant Professor in the Department of Mechanical Engineering, NIT Uttarakhand. My topic of presentation is numerical simulation of heat transfer and pressure drop in two different configurations of pin-fin microchannel heat sinks. This work has been carried out uh, by me along with my colleague Dr. Dungali Srihari. Now contents are as follows. Introduction. I will give some brief idea about microchannel heatsink, objective and problem definition, methodology, results and discussion, conclusions and reference. It is well known that with time, the tendency of miniaturization is increasing in various fields of engineering and technology, especially in electronics. At the same time, it is desired to increase the performance and output of the engineering devices. Henceforth, it becomes challenging to remove high density heat from a confined area. Inefficient cooling causes overheating that may reduce lifespan and damage the.
Hello, Viresh. Hello, hello, Viresh. Yani, hello, Viresh. Viresh का paper. Sound आ रहा है ना? Hello, Viresh. Yeah, Viresh, please. Hello, unmute yourself, Viresh. Hello, hello, Viresh. I can see your raised hand, but I not able to hear your voice. Please unmute yourself. Unmute yourself, Viresh. You will find the unmute button on the right top.
Just beside the leaf, you'll see the mic button. Right now, you are in a muted condition. That is, I'm not able to hear you. Hello, Viresh. I want to know your paper ID so that I can play it and you can see that. Yeah, Viresh, you raised your hand again. Please unmute yourself. Message. Hello, Viresh.
Hello, sir. This is Viresh. Hello, sir.
Yeah,
This is
Viresh.
Viresh.
Yeah, yeah, yes, yes, Viresh. Viresh.
Actually, I am using on my desktop. So
Okay,
its workstation doesn't have a microphone, sir. My paper ID is 28. You can play. I can hear it, sir.
okay. Paper ID is 28. Okay. Schedule मिल गया होगा इन लोग को? 28. Okay. Wait. Let me see in which. Okay, 28. I got it. I'm going to play that video. Okay. You just see
Okay, sir.
and confirm. That okay. Wait.
Hello all. Hello all. Hope everybody is
Hello, I am Viresh. Hello, sir. Taker, PhD student under Dr. K. Venkata Supaya in the Department of Mechanical and Aerospace Engineering at IIT Hyderabad. The topic of my presentation today.
Shit. Yes, Viresh. I just played your video. Okay.
Okay, sir. Okay, I will see it, sir. Thank you. Hello. Hello, sir. Are you there?
Hello, Viresh.
Sir, voice is not coming.
Voice is not coming.
Yes, sir.
Yeah,
I'm not,
okay, okay, wait, wait. Initially, was it coming?
no, sir. Initially, also it was not coming.
Okay, okay. Let me do this again.
For my presentation, it was not coming. Other presentation, it was coming, sir.
Okay, 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 okay. Now I guess it will come. Just listen.
So used channel. We have used the channel flow without the back pressure. Yes, and finally, the time indicator.
Now it's coming.
Yes, sir. Yes, sir. It is coming.
Okay. I'm continuing that video. Okay, you see.
Okay, sir. Okay, sir. Integration is achieved using Rangekutta fourth order schemes. Entire solver is developed in the Fortran 95 language.
अभी इतनी वॉल्यूम सफिशिएंट है नहीं नहीं
Into the
सब
boundary conditions.
सफिशिएंट है
Uniform velocity, pressure, temperature, density are specified at the inlet. Turbulent intensity at the inlet is 5%. Viscosity ratio is 5. No slip boundary conditions are applied for velocity field at the top and bottom wall. Turbulent kinetic energy is set to 0 at the top and bottom wall. Newman boundary conditions are employed to calculate the temperature, density, pressure, and specific dissipation rate at the top and bottom wall. Both the top and bottom walls are insulated, that is adiabatic boundary condition is imposed. All the flow variables except the pressure and density are extrapolated at the exit. The pressure at the exit of the channel is specified using the BPR, that is back pressure ratio, which is defined as the P exit by P in, which is defined as the P exit by P in, which is equal to 2 and 4. Density is computed using the equation of state to satisfy the mass conservation at the exit of the channel. Grid sensitivity and validation. Figure A highlights the variation of Mach number at the center line of the channel for coarse, medium, and fine grids for these inflow conditions. From the figure, we can see that as the grid size increases from coarse to fine, the solver is able to capture the flow physics. And for the results of fine grid, are matching well with the experimental results of Corel as shown in figure B. This corroborates that the results, the current solver is able to capture the flow physics. Furthermore, because of the complex nature of the flow, that is shock train formation in a channel or isolator, a stringent grid independent may not be possible. Hence, we have restricted to the study of grid sensitivity. Here I am presenting the effect of Mach number at BPR equal to 2. Here we specify back pressure ratio and vary the inflow Mach number to see its implications on the shock train structures. Let us first understand how the shock train structures are formed in the channel subjected to back pressure. The pressure originating from the inlet and the pressure originating from the outlet interacts with each other, and the interaction of these two leads to the formation of first shock or leading shock, which then interacts with the turbulent boundary layer at the top and bottom wall. At the interaction point, the boundary layer thickness increases and the propensity to separate of the wall depends on the shock strength. The boundary layer further grows under the influence of adverse pressure gradient created by the back pressure, leading to the flow confinement and eventually the formation of multiple shocks. These multiple shocks are characterized by series of oscillations as shown in figure A. From the figure A, we can see that formation of shock trains is present for all the Mach numbers, that is 2, 2.5 and 3, and the strength of the successive shocks reduces as we move from Mach 2 to 3, and the number of shock trains, successive shocks, also reduces as we move from the Mach 2 to 3 due to the presence of dominant streamwise velocity for higher Mach numbers, which assists in negating the effect of back pressure present at the exit of the channel. Figure B shows the variation of Mach contours for different Mach numbers. From the figure B, we can see that there is no substantial change in the Mach contours, but the magnitudes are different. Figure A highlights the mean wall pressure at different Mach numbers for BPR equal to 2. From the figure, we can observe that for Mach 2, the mean wall pressure increases steadily from the inlet to the exit, whereas for Mach 2.5 and 3, the mean wall pressure increases up to near to the exit and it eventually falls to the pressure specified at the back pressure specified at the exit. This indicates that for Mach 2.5 and 3, the streamwise momentum dominates the back pressure compared to Mach 2. Magnitude of density gradient variation for different Mach numbers is shown in figure B. The magnitude of density gradient is computed using this formula, which represents numerical Schlerin image. From the figure B, we can see that there is no substantial change in the contours of density gradient, but the magnitudes are different. Here I present the effect of Mach number at BPR equal to 4. Here we specify the back pressure equal to 4 at the exit of the channel and vary the inflow Mach number to see its implications on the shock train formation. Figure A highlights the variation of central line Mach number at different Mach numbers at BPR equal to 4. From the figure, we can see that at Mach number equal to 2, the shock trains are completely expelled out from the inlet, that is discoursed from the inlet, whereas for Mach 2.5 and 3, we can observe the formation of shock trains in the channel. Furthermore, we can see that there is a substantial change in the magnitude of shock trains for Mach 2.5 owing to the enhancement of boundary layer interaction. Mach contours variation for different Mach numbers is highlighted in figure B. From the figure B, we can observe the formation of shock trains for Mach 2.5 and 3. This study indicates that for Mach 2, BPR equal to 4, the shock trains are completely disgorged from the inlet, leading to the subsonic conditions in the channel, which may lead to the engine unstart because the entire regime is to be at supersonic conditions. Figure A highlights the variation of mean wall pressure at different Mach numbers for BPR equal to 4. From the figure, we can observe that for Mach 2, the wall pressure suddenly rises up to the value of back pressure specified at the channel exit. This clearly indicates that for Mach 2, the effect of back pressure specified at the exit of the channel felt up to the inlet, whereas for Mach 2.5 and 3, the mean wall pressure increases steadily from the inlet to the exit. The magnitude of density gradient contours for different Mach numbers is shown in figure B. From the figure, it is observed that for Mach 2, the shock trains are completely expelled or disgorged from the inlet, whereas for Mach 2.5 and 3, the shock train formations are observed. Here I present the effect of back pressure on streamwise velocity variation. Here we have plotted the variation of streamwise velocity along the wall normal direction at x is equal to 3L by 4 up to the channel center. From the figure A, B and C highlights the variation of streamwise velocity at BPR equal to 2 and 4. From figure A, we can observe that for Mach 2, as the BPR increases from 2 to 4, the boundary layer thickness reduces and there is a substantial change in the velocity magnitudes, that is higher velocity gradients are present at Mach 2 for BPR equal to 4. Similarly, at Mach 2.5, if I increase the back pressure ratio from 2 to 4, we can observe that there is an increase in the boundary layer thickness due to the shock boundary layer interaction. At Mach 3, the effect of BPR is not even felt. That is, there is no substantial change in the streamwise velocity as shown in figure C. Following are the important conclusions from the present study. For Mach 2, as the BPR increases from 2 to 4, the shock train structure is discourse, that is expelled from the inlet, forming subsonic conditions in the channel. For Mach 2.5, as the back pressure ratio increases from 2 to 4, a fewer number of shocks are absorbed, but with higher magnitudes as compared to BPR2. Higher boundary layer thickness is observed for Mach 2.5 as the BPR increases from 2 to 4. For Mach 3, the variation of BPR did not manifest in substantial change in the shock train structures as compared to 2 and 2.5. Acknowledgement. We thank organizers of FMFP 2020 for giving us the opportunity to present our work. We thank all the reviewers for their valuable suggestions in improving the quality of paper. These are the references.
Hello,
Hello, Viresh.
Hello, sir.
Did you find anything wrong in the video? Any voice
Actually, sir,
quality?
the same
Yeah.
voice quality is okay, sir, but the changing over from slide to slide is slow in the computer, but in the mobile it is coming very properly. I'm simultaneously like doing it in both the ways.
Okay, okay. No, actually, there might be some network lag is there. Maybe that is why.
Okay,
Otherwise, the whatever is written in the PPT everything is clear, I guess.
okay, sir.
Any
Okay, okay,
any issue
okay.
did you
That
find?
is written is clear. Yes, sir.
Okay, okay, okay. None.
Okay.
Okay. Sushanta Datta. Hello, sir. Sushanta Datta.
Good afternoon. Yeah, good
Hello.
afternoon.
Yeah, yes, sir.
Yeah.
Sir. Yeah. Yes, please.
সুশান্ত দা অমরেশ বলছি এই তো চলে গেছে
Actually, I don't know
সুশান্ত দা
why.
অমরেশ বলছি দিস ইজ অমরেশ
ও আমরেশ,
হ্যাঁ হ্যাঁ হ্যাঁ
হ্যাঁ
বলো
ঠিকই আছে, এটা ঠিকই আছে। আচ্ছা, তোমাদের যেটা ইসে বানিয়েছো, কি বলে তোমাদের বইটা যে বানিয়েছো, কি ই বুক
হ্যাঁ হ্যাঁ
যেটা করেছো,
হ্যাঁ
তাতে সেশন চেয়ারের মধ্যে আমার নাম দেখলাম না, কিন্তু এটা কি মানে জানি না কি ওটা।
না না সেশন চেয়ারে তোমার নাম থাকবে তো ওই যেখানে লাস্টে যে ইয়ে আছে না সিরিয়ালের
হুম
মধ্যে
হুম
নেই